So hello everyone, myself is Gautam Singh. I will be presenting a strange behavior of light through an experiment which defies the quantum mechanical behavior of light. So the title is Light Can Take Infinite Path from Between Two Points. So let's get start what it actually means. You have seen interference patterns, you have performed interference experiments, diffraction experiments throughout your bachelor's as well as in master's. So interference and diffractions are mostly same concepts. There are wave sources which we consider as the source. Then there are due to slits, or we can say deflectors, or we can say some kind of very fine string, secondary wavelets form which interfere, which give rise to constructive interferences and destructive interferences. In diffraction, it basically works on same phenomenon, but the output is slightly different. You see a fringe pattern with varying intensities as you go far away from the, let's say, central maxima. So this explanation can be a classical way, like we can explain these phenomena classically, but now we will be looking at bit more deeper into it. So to study the strange behavior of light, we will look into the quantum mechanical aspects. We have used the book Quantum Electrodynamics for this purpose, written by famous scientist Richard Feynman. Now we will use few concepts of quantum mechanics. First one is the path integral formulation. What it means is we integrate over the complete path whatever wave or a particle or a photon takes to results to get out actual information in terms of probabilities. So we say the probability of finding a monochromatic light wave at any point depends, quantum mechanically depends on the summation, like sum of all the amplitudes of each wave at that point. We sum it, we get the amplitude, and if we take a square of it, we get the probability of finding the photon, or we can say wave function at that point. So now let's look at the main picture or some basic picture before starting the explanation of the video or the experiment. Now let's say there are two paths, path A and path B. So a photon corresponding to its wave can take infinite number of paths from point A to B. All the possible paths in the picture you can see, whether it be a straight line, whether it be a curved path, whether it be a sinusoidal, cosine function, a path which goes from sun and back to point B is also considered. These paths are mathematically acceptable because they have a non-zero probability of existing. So let's look at few paths from point A to B. As you can see, so there are few 2 to 3 paths from point A to B, and there is a small vector which is associated with it. That special arrow represents the phase of these hypothetical paths. So and each wave is, again, electromagnetic wave especially, is present with their phase angle as well, or we can say a simply phase of a wave. So each wave has a few properties like amplitude, their frequency, their phase. So if we consider a monochromatic light, so we can say the frequency of all these waves are same. Second important thing you can see from point A to point B is each wave, or like I can say each particle takes a different path. So especially the path length of each waves are different. Now as speed of light is constant, distance between A and B is constant, what actually change is the time taken from each path. So this time taken from point A to point B is represented is, we can say, analogous to the phase of the wave. If the path difference of two waves are different, both the waves will have different path. And to sum the complete story, like because we get these vectors, to get out some information out of these vectors, again we take a resultant vector, we align each vector from tip to toe, and we see a resultant vector. That resultant vectors we can take a square, or we can say modulus, which results a sensible quantity which we can say as probability of finding. So probability of finding a wave depends upon the square area of the square. More the area will be, higher will be the probability, and more we can say probability of, we can say, detecting a photon at point B. So the length of total arrow is given by summing of amplitude, that is the summation of all the amplitudes from point A to point B, and red square say is the probability. Bigger the square, higher the probability, smaller the square, lesser the probability. Now moving next. First case, all the paths are very closely packed, and in case B all the paths are winding and none of the paths are let's say straight. Below there we have individual vectors, phase vector, what the vector which represent the phase of each path from first case and for second case as well. Now again, if we align each vector from the tip to the arrow, one back to another, we get two different vectors. So the red line from one tip to another tip is a vector, and the second case is a vector. The difference you can see is how huge of area is covered by each square. Basically, if you take a square, or we can say a resultant vector, and sum it, you get a probability. So what these two cases result is, for a light from point A to B, we will have higher probability. But if light waves are hypothetically taking winding paths from point A to point B, the probability decreases drastically. Like this area of that square, or we can say the probability of finding that photon at point B via taking those many points, curvy and scribbly paths, is very less. Therefore, classically we say light takes a straight line rather than a curved path, because a straight line has a higher probability of having detection of light at point B, while a path which takes a curvy line. So the probability of such light waves seeing or detecting is very small. Now let's move to the next point. So now this is some basic concept. We will be looking at the experimental setup of the experiment which I have performed. So we have used a laser source, HENE laser, from department itself. Second, we have recorded this video, or like let's say the experiment on phone. So the second is the phone camera. We have used a thin mirror, or in the experiment I will be highlighting what shape of the mirror is. Then we shine a laser light to a mirror and it reflects. So classically the angle of incidence and angle of reflection are same in both the cases. Now, being a laser, it has a very less beam divergence, especially very small. The beam doesn't spread in all direction, it stays in one particular direction. It has a very high directionality. That was the reason why we used laser, to give a special property to the light. Second thing which comes in the picture is the diffraction grating. I have placed on the left side of the mirror, and we covered the half part of the mirror with a black paper, so that none of the light rays are reflecting to the mirror. So actually what we see is a spot where the light is hitting on the paper, which we will see in the experiment as well. So before looking to the experiment, we, from let's say very small age, from our primary school, we are learning that if we shine a laser from a mirror, let's say this is a mirror, this is a laser, it will have a single point on the mirror and it will be reflected back somewhere. That's all we observe and that's all we see. So somewhere I will be proving that this is not actually what happens. If we see a spot here of a laser, we will also see a laser reflecting from here as well, here from as well, and theoretically from every point of the mirror we can see a laser, a highly directional beam to be reflecting. That is the experiment which I am showing, and I want to prove that light actually does not reflect from one point but from all the points. Even if it is a laser, it is a very ideal laser, it will reflect from all the points on the mirror. This is the statement. As you can see, so this is your helium neon laser right there. I have placed it on sand, holding it. Now as you can see, this is the diffracting mirror as well as with a diffraction grating. So the speciality is it has a reflecting surface, but as you can see in the central section, it has a grating or grooved lines which helps reflecting the light as well as diffracting it. So classically, if we reflect a laser light on the mirror, as you can see, there is a point in between, as you can see right here, and further in the video you can see a reflected beam. That's all we know, we see happening in our day-to-day life as well. So this is the setup. You can see a reflected. If we switch off the light, you can still see a laser source right here. Now, yeah, so now I have covered it with a black paper, so it doesn't reflect anymore, it doesn't hit the mirror. That is the key thing which we want to make sure in our experiment. So it is not hitting in the mirror, and this is the diffraction grating which is on the left side of the mirror as shown in the experiment. So this is the covered paper and this is the diffraction grating, and the whole surface is the mirror. Now classically what should happen, as the main beam is here, right here in the blue dot, as you can see, so we assume light is reflecting on the covered part, right? But ahead in the experiment you will see the reflection on the uncovered part of the mirror, especially on the diffraction grating. But it doesn't make sense, right? Beam is reflecting here, so the point of hitting a laser beam is right on the covered part. So with our eyes as well, we don't see any of the rays, light rays hitting the uncovered part of the mirror. It's not like an extended source, so it have rays going in all, spreading in all directions. It is a directional, so the spread of light is very less, so we shouldn't see any reflection. That's what we have heard from all the times in our schools, in our bachelors as well. But this experiment actually shows that you can still see a reflected, a very tiny reflected mirror spot on the diffraction grating. So let me play the next video and see what happens. So this is the complete video. We will switch off the light. Yeah. So this is the covered part, as you can see. Let's pause for a bit. This is the covered part. This is the reflected, or we can say the point of incidence where the laser light is pointing at. So it is far away, pointing from the uncovered part, which is placed like where is the grating element is present. So it is reflecting here. That's my finger, so it is brightening so much, so it has a very thin small spot. Now keep an eye on the grating element and let's see what we observe. So this is the point of reflection. We shouldn't observe any kind of laser spot beyond this point. So let me play and watch it. So as you can see, there is a reflected point on the mirror. How cool is that? Like, on the main beam is reflecting on the covered part, but again we have seen a second reflection. It's not any kind of like secondary maxima or that kind of thing. We are directly pointing it on the covered part, so there is no point of secondary reflections or any kind of thing. This covered part is perfectly opaque, no light is even passing. And being a directional source, the laser light doesn't have even spread in all directions, so most of the light rays is coming at the covered part, and but you still see a tiny spot appearing on the grating element. Like repeat this video and you can see again, you can spot it right here. You can see a tiny spot appearing on the grating element. How is that possible? Like, we have shined a laser on the non-reflecting part and we are seeing a laser light, like a laser light which is reflecting on the grating. Like, it doesn't follow the Snell's law in principle, or we can say angle of reflection should be equal to angle of incidence. So that is broken because you have a second point of reflection as well. Main point is on the covered part, but you see a second point of reflection on the grating element. What this proves is light actually doesn't follow one ideal case where it has to follow some angle restriction, like the angle of incidence should be angle of reflection. That what is the consequence if we, so I will give a proper explanation. If we'll assume a light is taking infinite number of paths before getting to point B, before reflecting from the mirror, like each path is probable. If there is a plane mirror, all other reflections, or we can say probabilities of paths, are gone. But this what proves is the laser source, the waves, the photons from the laser actually hit every part of the mirror and reflect back. We don't see from every point because the probability of seeing, the Y probability is low because the amplitude at that plane, or we can say reflecting points on the mirror, is very low, or we can say 0. Therefore we can't see any reflection. Let's look at this once again. See this huge phenomenon. You can see a second reflection from the grating. So this is again, that's the laser pointed right there, and you can see a secondary reflection appearing on the grating element. That is like mine, like all your maths and science, what you have learned is changing. So first assumption from this picture is the green light, which actually is what we observe from a point of reflection. But if we assume, even if a laser source is very what you say, directional, a directional beam can still take all the paths possible from this mirror, reflecting from every single point on the mirror. So as you can see, this path and this path have same path difference. So different paths have different path differences. Previously in the video you have seen a path difference is directly related to the phase. If path difference changes from 2 points, if a rays have traveled a different path, it will have a different phase. So in the left region, as you can see, this region, we have such kind of vectors, and in this region we have this kind of phase vectors, or some vector pointing the phase. Now if we join it again from tip to toe and we construct a probability square, the probability is very low, like very less probability. So any photon finding we find in this region is very less. Same goes with this region. Probability of finding a photon, we can say a chance of reflection from this region is very less. Now we look at central region, where it actually classically we assume to be reflecting. All the phase vectors are in same direction, which means there is hardly any phase change. All the waves are reflected and reflected back to the camera, incident and reflected back to the camera. So if we add these vectors from tip to toe, you can see a huge probability square. So the amplitude is very large, which means we have seen the light there, because in terms of amplitude, where the amplitude is largest, we see a reflection appearing there. So that is the reflection point, which follows angle of incidence is angle of reflection law, all the angles law and all the classical properties. So that's where we see a laser point in our observations as well. So why this region has zero reflection? Because these vectors basically cancel out each other. They are oriented in such a way like the net resultant vector is 0, and we have a very zero amount of probability. Let's see one better picture to explain. So this is some cross section of mirror, where this is all the points of reflection, assuming that light take all the possible paths of reflection before reaching the camera. So as you can see, these are the vectors which curls up in the circle, and the resultant vector of a circle tends to 0. Therefore we don't see any reflection from the point which is not the angle of incident point, or the point where it is actually reflected. So how in the grating we are seeing? Imagine, let's see a second slide. So this is the first slide. Imagine we block some of the light which is reflecting. So let's say this is the point of reflection, this is the scale. Let me check if I have something to demonstrate. So let's imagine this is the scale. So all the points are reflecting as shown in the picture. So all the vectors, if they are add up, they will be 0. But if we block some parts of the reflecting beam, the sum of total vectors will be non-zero, because that reflected parts are missing. Same thing we are done here. We have blocked some sections of this. So best tool for blocking n number of waves is by using a grating. So we placed a grating on the mirror which blocks some part of the light and allows some part of the light to reflect. So the resultant vector, as you can see, which are blocked, there will be no phase addition. Which are not blocked, there will be a phase addition. And if we add the total vector, we will see a non-zero phase vector, a non-zero phase, which again corresponds to a non-zero amplitude. So this all discussion is not for the apart from the point of reflection, because the reflection is on the black bodies. This is all happening on the mirror. So from here, by placing a diffraction grating, we actually block some of the waves, or block some of the probability vectors from adding. So the net addition is not 0. Due to non-zero addition, we have a very finite amount of probability, or we can say finite vector, resultant vector. The square of the resultant vector again gives some probability. So if a place on the mirror which has non-zero probability, which means which has a non-zero amplitude, which means there is a reflecting light. So even if you shine a laser on the covered part, due to if you don't use a grating, you see no reflection on the mirror, because everywhere the phase vector cancels out and the probability is 0, the amplitude is 0, and there is no reflection. But if you place a grating, it passes, it blocks, so creating a non-zero reflecting surface. So some part reflects, some part not reflect. The reflecting part phase vector will add up, non-reflecting part phase vectors will not add up. So because of it, because of a finite magnitude, it has a finite amplitude, which means a wave having an amplitude means we can see a light to be reflected from that point. So this actually proves gives a new thought idea of how we understand our world, and gives a quantum mechanical picture of the light wave, and it reveals different phenomena. So I would like to, so this is my OGT experiment, video presentation of what I have did. I would like to thank Professor Dipti ma'am, my OGT guide, which have looked after this, managed all this, given me an opportunity to present this experiment in front of all of you. Then I would like to thank Professor A.G. Banpurkar sir. He have provided with all the apparatus required, starting from lasers to gratings to mirrors. I would really like to thank Department of Physics for providing as well, and I would like to thank my friend Harleen and Tamojit for helping me to carry out experiment, and Tamojit for recording the experimental video. I would like to thank. So thank you very much. Thank you for giving this opportunity.